Hi, this is Hilal. In this video on mathematical economics series, we will try to solve a problem on constant elasticity substitution production function that was asked by a brother Ifamo Joseph on Telegram channel. The question is like this. We have to maximize CES production function. We are being given a CES production function that is Q is equal to 75 bracket 0.3 k to the power minus 0.4 plus 1 minus 0.3 L to the power minus 0.4 whole raised power minus 1 upon 0.4. This is our CES production function and it is being subject to the constraint that is 4k plus 3L should be equal to 12. Sorry, it is here 120. Okay, so we need to maximize this production function with the given constraint. That means 4 times capital plus 3 times labor should be equal to 120. Okay, now basically what is the CES production function? The general form of CES production function is given by, first I will tell you the general form, then we will optimize this very function. Okay, CES production function is given by, that is Q, that is quantity, is equal to A alpha k to the power minus beta plus 1 minus alpha L to the power minus beta raised power minus 1 upon beta. Okay, this is the general form of the CES production function, and here this A is greater than 0 and alpha lies between 0 and 1. Okay, and this beta is greater than -1. Okay, now what is this alpha? This A denotes the efficiency parameter. This is our efficiency parameter. Okay, it shows the state of technology. Okay, and this alpha denotes the distribution parameter. Okay, this is a distribution parameter, and it denotes the factor shares of capital and labor. Okay, now what is our this beta denotes the substitution parameter. It is substitution parameter. Okay, and actually it is used in determining the value of the elasticity of substitution at this beta. Okay, so actually I have made a video in full detail about the CS production function. You can find in the info of this very video, that very video. Okay, so I will not go into the details of this CS production function. Let me rub this out. I was just clarifying what is this. 75 is A, similarly minus 0.4 is our substitution parameter. Okay, this 0.3 is our distribution parameter here. Okay, so let me rub this out and we will solve the CES production function with the given constraint. Okay, how do we do that very thing? It is very simple. First we write our CS production function, that is Q is equal to 75 0.3 k to the power. If I just write them in fractions, okay, to save the space I will write them in the fractions. So this will come out to be minus 2 upon 5. Okay, this 0.4. Okay, now similarly we have 1 minus 0.3 will come out to be 0.7. It can be written as 7 upon 10. So I will write here 7 upon 10 in place of this very thing. Okay, let me rub this out. So this is 7 upon 10 L to the power minus 0.5 can be written as 2 upon 5 whole. This minus 1 upon 0.4 can be written as 2 upon 5. If we take it as reciprocal, so this will become minus 5 upon 2. Okay, so I will write here this is minus 5 upon 2 here. Okay, this is our production function, and our constraint is subject to the constraint, that is 4 times capital plus 3 times labor should be equal to 120. Okay, how do we optimize this? First this production function, this is called the objective function. Okay, this is called the constraint function. First we need to form the Lagrange's function. How do we form the Lagrange's function? First we set this constraint equal to 0. Okay, and after that we multiply it by lambda. Okay, I have shown the constraint optimization methods in n number of videos. You can just check the video this channel. You can find very good videos on the constraint optimization. Okay, if we set this first, if we set this equal to 0, so this will become 120 minus 4k minus 3l is equal to 0. After that we multiply it by lambda. Okay, now our Lagrange's function is simply this objective function plus this resulting constraint function, which is multiplied by lambda, and obviously first setting it equal to 0. So we have 75 0.3 k to the power minus 2 upon 5 plus 7 upon 10 k to the power minus 2 upon 5 raised power minus 5 upon 2. Uh, to this objective function, we add this resulting constraint to form the Lagrange's function. Okay, so adding this, that is lambda 120 minus 4k minus 3l. Okay, so this is our Lagrange's function. Now first order conditions for optimization requires that we take the partial derivative of this Lagrange's function with respect to L, K and lambda and set them equal to 0 simultaneously. Okay, so first we need to, so first order conditions are we take the partial derivative with respect to capital, that is, and set it equal to 0. L subscript k denotes here the partial derivative with respect to capital. Okay, now we need to differentiate this very Lagrange's function with respect to k. Okay, so we have this very function here. We will use generalized power function here. First, how do we differentiate? This exponent becomes our coefficient, so we have 75 into minus 5 upon 2. Okay, then we have here 0.3 k to the power minus 2 upon 5 plus 7 upon 10 k to the power, sorry, it is here L to the power, so we have L to the power minus 2 upon 5. Okay, then we have minus 5 upon 2. To this we subtract 1. Okay, this is simply by the power function rule. If we have x to the power n, it is derivative, simply this n becomes coefficient and x is subtracted, that is the exponent is subtracted by 1. Okay, I have shown it in so many videos. Now this was the exponent part, and then we need to internally differentiate, so we are left with this very term. Okay, and again taking derivative of this term which is in the brackets. So what will be the derivative of this very function, this very term here? Similarly, this exponent will become coefficient, so 3 upon 10 I can write it like this, uh, 3 upon 10. Okay, then we have this exponent, that is minus 2 upon 5. Okay, k to the power minus 2 upon 5 minus 1. Okay, I am just internally differentiating this very thing. Okay, then what is the derivative of k here? The derivative of k is 1, since no k is involved in first term and last term, so their derivative will be 0. Now 4 into lambda, so we have minus 4 lambda is equal to 0. Okay, I hope I am making sense here. Now we can write it like this. We have 75 into minus 5 upon 2, taking these terms here, so we have 3 upon 2 into minus 2 upon 5, and we are left with so in place of this I will write 3 upon 10 k to the power minus 3 upon 5 plus 7 upon 10 L to the power minus 2 upon 5. Now if we subtract minus 1 from minus 5 upon 2, so this will become minus 5 minus 2 is minus 7 upon 2. Okay, and obviously we have k to the power minus 7 upon 2, and we set it equal to 4 lambda. Okay, we just transpose this here. Now what can we do? Here at this 5 and 5 will get cancelled, 2 and 2 will get cancelled, so what are we left with here? Am I doing the right calculation here? So we have 3 upon 10 here, okay, and 2 upon, so actually it is here 3 upon 10, okay. Now we have 5 twos are 10, 5 ones are 5, 6 7 5 fives are 25. We have 15 into 3 is 45, minus minus is plus, so 45 upon 2. So we are left with 45 upon 2. This very thing, that is 3 upon 10 k to the power minus 3 upon 5 plus 7 upon 10 L to the power minus 2 upon 5 raised power minus 7 upon 2 k to the power minus 7 upon 2 is equal to 4 lambda. Okay, we have just differentiated this Lagrange's function with respect to k. Okay, again we need to differentiate with respect to L. Okay, now if we differentiate with respect to L, so what will be our answer? Now first thing is same, this exponent will become coefficient, so we have 75 minus 5 upon 2, okay, then we have 0.3 k to the power minus 2 upon 5 plus 7 upon 10 L to the power minus 2 upon 5, this will remain same, and this exponent will be subtracted by 1 by power function rule, so we have minus 5 upon 2 minus 1. Okay, now we need to internally differentiate with respect to L. So we have here 7 upon 10, so we have 7 upon 10, this will become coefficient, so this will become minus 2 upon 5 L to the power. Now if we subtract minus 1, because we are using the power function rule here, minus 2 upon 5 minus 1, what is minus 2 upon 5 minus 1? This comes out to be minus 7 upon 5 again. Okay, so we have minus 7 upon 5. Okay, so I'm just skipping one step here. Okay, now let's take these terms here. So we have 75 into minus 5 upon 2 into, we have this 7 upon 10 into minus 2 upon 5. Okay, and we are left with here 0.3, so I will write again it as 3 upon 10, okay, to make it beautiful here. Okay, so we have k to the power minus 2 upon 5 plus 7 upon 10 L to the power minus 2 upon 5. So this will come out to be minus 7 upon 2, this power, and then we have minus L to the power minus 7 upon 5. Okay, here 5 and 5 will get cancelled, 2 and 2 will get cancelled, so we have again 5 2s are 10, 5 15s are 75, 50 15 into 7, but it comes out to be minus, and minus will become plus, so we are left with 7 5s are 35, 7 ones are 7 8 9 10, so this is 105 upon 2, 3 upon 10 k to the power minus 2 upon 5 plus 7 upon 10 L to the power minus 2 upon 5 raised power minus 7 upon 2 L to the power minus 7 upon 5. Okay, did I miss it here something? Yes, actually I missed it here this very thing, because we were differentiating with respect to k. So we have here sorry, with respect to L, so the derivative of L will be 1, so we are left with minus 3 into lambda is minus 3 lambda, since no L is involved in the first two terms here, so their derivative will be 0. Okay, so actually we have here minus 3 lambda is equal to 0, minus 3 lambda is equal to 0, minus 3 lambda is equal to 0. Okay, now what we need to do, now we need to take the derivative with respect to lambda. Okay, so L of lambda, so taking the derivative of Lagrange's function with respect to lambda, that means since no lambda is involved in the first term, here the derivative of lambda is 1, so we are left with 120 minus 4k minus 3l is equal to 0. Okay, let this be equation first, let this be equation second. So let me transpose it here. Okay, is equal to 3 lambda. Let it be equation second and let this be equation third. Okay, I hope it is getting messy here. So now we need to find the optimal values of L and K. Okay, how do we find the optimal values? So if we divide equation first by equation second, so if we divide equation first by equation second, so what is equation first? This is 45 upon 2. We have 3 upon 10 k to the power minus 2 upon 5. Okay, actually I have written 3 upon 5 here, sorry. So 2 upon 5 plus 7 upon 10 L to the power minus 2 upon 5 raised power minus 7 upon 2. Okay, and to this we will divide equation second, that is 105 upon 2. This is same, that is 3 upon 10 k to the power minus 2 upon 5 plus 7 upon 10 L to the power minus 2 upon 5 whole raised power minus 7 upon 2. Okay, this is the LHS. So what is in RHS? We have 4 lambda and 3 lambda. So we have 4 lambda upon 3 lambda. Lambda gets cancelled. Here we can see these terms are same here, so we can cancel these very terms here. So we are, sorry, I forgot to write here this k to the power. So we have actually this term also, k to the power minus 7 upon 2, and here we have L to the power minus 7 upon 2. Okay, so when we subtract, when we cancel these two, what we are left with, we have 45 upon 2 into, if we try reciprocate, this will become 2 upon 105, and here we are left with k to the power minus 7 upon 2 and L to the power minus 7 upon 2 should be equal to lambda gets cancelled. We are left with 4 upon 3. Okay, so here 2 and 2 will also get cancelled. And what can we do here? So we are left with 45 upon 105. What is 45 upon 105? So this is 5 nines are here, we have 5 2s are 10. Okay, so here we have 5 nines are 45. So here we have 5 2s are 10, 5 1s are 5. So we are left with 9 upon 21. So we have 9 upon 21. Okay, if we reciprocate these terms, the exponent sign will get changed. So if it is k to the power minus 7 upon 2, if we take it to the denominator, it will become plus, that is k to the power plus 7 upon 2. Okay, similarly if we take this L to the power minus 7 upon 2 to the numerator, the exponent sign will get changed. Okay, so we can write L to the power 7 upon 2 here. I am just reciprocating numerator and denominator, and we have k to the power 7 upon 2. Okay, is equal to 4 upon 3. And if we further solve this, this will come out to be 3 3s are 9, 3 7s are 21. I hope I am making the calculation right here. Okay, so we have 3 upon 7. We can write L upon k to the power 7 upon 2. Okay, is equal to 4 upon 3, or we can write L upon k raised power 7 upon 2 is equal to 4 upon 3 into it will get reciprocated. So this is uh, this will become 7 upon 3. So this is 7 4s are 28, 3 3s are 9. So this is 28 upon 9. Okay, so L upon k raised power 7 upon 2 is equal to 28 upon 9. Okay, Now if we transpose this exponent, this will get reciprocated, this exponent will get reciprocated if we transpose this to RHS. Okay, that means L upon K is equal to 28 upon 9 raised power 2 upon 7. Okay, or we can write here, if we solve for L, that means L is equal to, if we transpose, it will get multiplied, so we have 28 upon 9 raised power 2 upon 7 into K. Okay, now we need to plug this very thing, L is equal to this very thing, in our third equation. Okay, so if we plug the value of L is equal to 3 in this equation, so we have 120 minus 4 in place of, so 4 K minus 3 in place of L, we have this 28 upon 9 raised power 2 upon 7 K is equal to 0. Okay, now this is 120 minus 4K. Now this thing will come out, if we use the calculator, this will come out to be actually I have calculated, this comes out to be minus 4.1K is equal to 0. So this is here we have 120, now minus 4K minus 4.1K, this becomes minus 8.1K. so if we transpose, this will become plus 8.1K. That implies K is equal to 120 upon 8.1. That means the value of K, the optimal value of K comes out to be, if we divide 120 by 8.1, it will come out to be 14.8. Okay, that means the optimal value of capital in this optimization problem will be 14.8. Now we need to find out the value of, let me rub this here. Okay, I'm hoping that I have made the calculation right. Okay, so I guess I have done the calculation right. So K is equal to 14.8. Now we just need to put, so we got K is equal to 14.8. We just need to plug this value again in equation third to get the value of L. So we have 120 minus 4 in place of K, we have 14.8. 14.8 minus 3L is equal to 0. So we have 120 minus, so this comes out to be 8 4s are 32, so this comes out to be 2, so we are left with 4 4s are 16, 17, 18, 19, so we have 9, so 4 ones are 4 and the kg was 1, so it is here 5, so 59.2. If we transpose, this will become 3L. Okay, now we need to subtract 59.2 from 120. This will come out to be, if we take 0 here decimal, so 10 minus 2 comes out to be 8. Okay, so we have 9 minus 9 is 0, so we can write here 0. Then 11 minus 5, 11 minus 5, 6 7 8 9 10 11, this comes out to be 60.8 is equal to 3L, which implies L is equal to 60.8 upon 3. Okay, so what is 60, this is 3 3 2s are 6, 3 zeros are 0 point, we have 3 2s are 6. Okay, and then if we take 3 2s are 6 7 8, if we take another 0, so this becomes 3 6 are 18. So let us confine with only 20.2. Okay, that means the optimal value of L will be 20.2. Okay, I have rounded off, I have just solved it for the one decimal place. Okay, that means the optimal value of capital optimal value of capital will be 14.8 and the optimal value of labor will be 20.2 in this constant elasticity substitution production function. I hope I make myself clear in this video, and the calculation is right. Okay, so if you like this video, please share, subscribe, and also if you want to donate to this channel, you can also donate via PayPal. Okay, it is just a free initiative for you people. Okay, thank you.